Okay, hello everyone. My name is Joao Pereira, and I worked with Dr. Kihan this summer on a molecular dynamics simulation of copper-silver alloys. I did this using a program called LAMPS and Oviedo, and I was able to study how that system interacted when the system energy was minimized. So LAMP stands for Large Scale Atomic Molecular Massively Parallel Simulator, and that's basically a big acronym to indicate that it just helps simulate how the atoms interact under different circumstances. And the purpose of this was to improve the performance of current conductors, since current conductors already use copper-silver alloys, and they've been in use. You can see here on this little figure that the inner three rings are made of copper and silver. Copper-silver are good matches for this because of their high strength and high conductivity. I use potential files that I gathered from NIST, the National Institute of Standards and Technology, and I imported them into the LAMPS software to simulate the model of the copper and silver being put under tensile stress. Oviedo, the open visualization tool that I used, was useful for me to tell that simulation was going according to plan. And as you can see, there's these little white slips of the atoms that shifted after the simulation versus before they were all just clumped together and unmoved. So I specifically looked at how copper and silver reacted at different temperatures. I inserted a silver fiber into copper atoms, and I looked at it around room temperature, which is 300 Kelvin, and at a higher temperature at 800 Kelvin. Important takeaways from this were that at a lower temperature, copper and silver were very isolated, and that before it was put in tension, and then after it was put in tension, copper actually dissolved into silver atoms at a room temperature, and it still showed those little slips. Furthermore, at a higher temperature with 800 Kelvin, the solubility of silver in the copper had already increased even without tension, so copper atoms were already dissolved into silver atoms even before the system was put in tension. And as the system was put in tension, even more copper atoms dissolved into silver. The purpose of this was just simply to improve the performance of magnets, so we have a better guideline for how these copper-silver alloys react under ideal temperatures and also under different temperatures than that they might be exposed to. After raising the temperature at 800 kelvins, it was useful to note that the silver atoms actually dissolved into copper without tension, and that's the big difference between the two temperatures, which was the main goal, the main observation of my project. I want to take a moment to recognize and thank Dr. Kihan and all my REU peers for an amazing summer. Thank you.